In this video, we're going to discuss what's called scalar multiplication of vectors. Now, what do I mean by a scalar? We'll generally use that term to mean a real number because it's a real number that we apply to a vector to scale the vector. So real numbers will oftentimes be referred to as scalars. Scalar multiplication is an operation that we perform on vectors. We take a scalar, a number, and we multiply it by a vector to get a new vector. So let's say that C is a real number, it's some scalar, and I take V to be the vector whose components are V1, V2, and V3. That's some vector in 3 dimensions. C times V is going to be the scalar multiple of C and V. That's a new vector, and all I do in terms of components is to take the components of the vector and multiply each one by the same scalar C. We are rescaling the vector. If my vector v looks like that, and I say apply a scalar, like for example, if I double the vector, if I go 2 times v, then I'll get a vector whose components are twice as much as the original vector, and there'll be a vector pointing in exactly the same direction, but have twice the length now. If I look at minus v, and by that I mean scaling by -1, that'll be the vector with the opposite components of my original vector, minus v1, minus v2, and minus v3. And that's going to be an identical vector, but pointing in the opposite direction now. Same length, but opposite direction. That's minus v. If I take 0 times v, I'm just going to multiply all the components by 0, and as a result, I'll get the 0 vector. And that's one of the reasons why we need this special vector, the 0 vector, because scalar multiplication can naturally result in it. If I scale a vector, it's going to affect the magnitude of the vector. We were discussing that intuitively a moment ago, but let's do that precisely now. So if I take a vector c and I scale it, a vector v, and I scale it by a number c, and let's look at its length. So what I have to do is take the components of that scaled vector and sum up their squares and take the square root. So it's going to be c v1 squared, c v2 squared, c v3 squared, add them all up, take the square root of that. Every one of those terms has a c squared in it, so I can factor that out. So it's c squared times the sum of squares of v's, and I take the square root of that. And now I'm multiplying under the radical, so I can start to extract square roots. And I know the temptation here is to take the square root of c squared and give me c, but you got to be careful. If c is a negative number, we're going to get its absolute value there. In general, the square root of a square is the absolute value of that number. And then it's times the sum of squares of v's, which is the length of v there. So what do we get? We got something very natural. The length of the scaled vector, so the length of c times v, is the magnitude of c. In other words, the absolute value of c times the length of v. So over here, if I take the length of 2 times v, I'll get twice the length of v, as you would have expected. There's a very important operation that we'll call normalizing a vector. We'll do it routinely. Whenever we're concerned only with the direction of a vector and not concerned with its actual magnitude, we'll frequently want to normalize it to get rid of the contribution of the magnitude and focus more on the direction. And so what do I mean by this? So I take a vector v. I'm going to assume it's a non-zero vector. In other words, at least some of its components are non-zero. Its length will be non-zero. And what I'm going to do then is scale that vector by 1 over the length of that vector. And because it's a non-zero vector, I'm not dividing by 0 here. So I'm going to take 1 over the length of v times v. That's my c there. And it's going to be, in just shorthand, we're going to take v over the length of v. And that just means to take each component of v and divide by the length. And that is going to be now a vector that's going to have the same direction as v. So v over the length of v will have the same direction as v, but it will now be a unit vector. And that's because of this principle up here. I am taking c to be the reciprocal of the length, so I'll have 1 over the length of v here times the length of v here, and they'll cancel out, and I'll get 1. So guaranteed to get a unit vector in this situation. And this process of taking a vector v and scaling it by the reciprocal of the length is called normalizing the vector. If that's my vector v and say it's very long, maybe it's 5 units long or something, then you should imagine that the normalized vector is this vector starting at the same point, but now it has a length of 1 unit. it will be common practice then to refer to this normalized vector as the length, or rather as the direction of the vector v. So if I ever say, find me the direction of a vector, I want you to normalize and just obtain that unit vector that's pointing in the same direction. And we'll use unit vectors exclusively to describe the length, or rather the direction of a vector.